Hello everyone. Um, my name is Aurobindo, and uh, I've seen that there are many people who have joined. Can you let me know, am I audible and is my screen visible? If you can type in the chat window, that will be helpful. Okay, got it. Thank you. So as of now, there are 28 participants. I would like to begin on time because there are a lot of contents. And as the people join in, maybe um, we can recap for them. For now, let me go through some of the housekeeping things. Number one is this is a long presentation, quite in depth. So, for the sake of proper Q&A, I would request you to hold your questions towards the end, right? So, for now, kindly put your phone on mute, and from my side, I will mute all the audience. Okay. So, you can still hear me, right? Okay. Um, the second one is the format in which this session will go is basically there are four sections, and in at the end of each of the section, I will pause for 2 and 3 minutes. I look at the chat window and try to answer your questions. But for interactive sessions questions, I have last 10 minutes where you can ask questions via chat or over the phone. But there will be questions, I'm sure, which maybe I cannot answer. In those cases, I'll keep those questions in parking lot and I'll get back to you in 1 to 2 days. Um, there may be some logistics issues. Then direct it directly to the moderator. His name is Mayank, and if you see the previous slide, this is Mayank's email address, or you can type in the chat window. And as I said, and as it was mentioned in the invite, this is a deep dive session. So you will really benefit from this session if you have prior experience in Redshift. Though um, a prior experience in Redshift is expected, even if you have worked in any kind of MPP like Teradata, then it will also be helpful. Okay. But keeping in mind that people might have worked quite some time back, I have kept the first section, which is a recap. Okay. Okay. Now, just to go through my profile, my name again is Aurobindo, and I have been working as a specialist for the data practice out of Bangalore. And I have been working in the industry for 17 plus years, close to 18 years now, and worked in different organizations. My background is mainly from the data modeling, data warehousing area. I've been working in AWS cloud for last 7 years, and particularly on Redshift and NoSQL technologies. Mm, Coming to the agenda, as I said, first 10 minutes will be for recap for the people who have worked on Redshift earlier or have worked on similar technologies. Um, Next section is in order to understand performance tuning, which is the focus of this session. This session is not about how of teaching you Redshift. It's assumed that you know Redshift. This session is a specific one on query tuning and performance optimization. We need to understand how Redshift interprets a query, okay, and how Redshift tries to tune the query performance. There are tools like Explain Plan is one of the tool with which you can analyze such optimization technique. And in the third section, where we'll spend most of the time, is on the best practices. And when I say query, many people think it's about selecting results from the database. It's really not so. Query goes as DMLs to create tables. Even your data loading, when you insert the data, everything under the CRUD, create, read, update, and delete, including the data modeling and table creation, contributes to the query performance. Okay. And then we will have some tutorials. Now, out of that, I was practicing how long each of these tutorials take. these tutorials are lengthy tutorials, so I kept one of the tutorial as an assignment for you. I will share what I have done here and share some of the outcomes of this tutorial around table designing, but the one around data loading I will do today in the class. Rest, there are two other tutorials which you can try, and there are links for that. How do you handle workload management in queries? So I have given link for those. Okay, sounds good. Any questions before we start? You can type in the chat window. We have now close to 50 participants. Okay. So let me start with the first section. And again, this is for the people who have either worked in Redshift or any similar MPP technologies. I would like to take you through a 10-minute recap. Now, in case you haven't, so I've shared this deck. This might be your starting point, right? In case you're completely new to Redshift, you can use these links to understand what Redshift is. But this was more of a session prep earlier. Okay, so let's understand what is Redshift. So Redshift is a Amazon managed, partly your responsibility, a customer responsibility as well. But from infrastructure wise, it is Amazon managed, a petabyte scale data warehousing service, which is hosted in Amazon Cloud. Now you can store a data in gigabyte range as well. Typically, customers stores data in terabyte range, but Redshift can scale up to petabyte range. Basically, it's a warehouse technology for running your BI tools on top of that. One of the most common question when I talk about any technology is where does it sit, right? Like Amazon, as of last reInvent, I mean day before yesterday, they announced like there are 159 to 160 services available. So among all the services available on cloud, where does Amazon's Redshift sit, right? Now, if I focus on this particular architecture on the right side, you'll see Redshift as a warehouse, data warehouse, a database, right, can get data primarily from something called S3, which is an object storage in Amazon Cloud. So this is primarily where your data lake gets formed, right? Now, data come to S3 from various places. It can be from your corporate data center. You can load your files as multi-part files. You can bring your data from the databases, and there are services for that, right? You can, for the bulk data movement, there are things like Snowball, where you can, it's a device where you can copy your data and send it to S3. But for Redshift, typically people use S3 as their source. So there is a specific, this arrow, which is a blue one, will be the primary data channel for getting the data inside Redshift. And there is something called a copy command, which is recommended and the most efficient way of pushing data from S3 to Redshift. Apart from S3, Redshift can get its data from DynamoDB. DynamoDB is a NoSQL database hosted by Amazon. It can get data from Hadoop, and Amazon's Hadoop basically is hosted in EMR, Elastic MapReduce, or it can get data from, say, a on-prem or EC2 machine. Okay, so and on top of Redshift, you can access the data through your BI tools using ODBC, JDBC connections. Let's understand the architecture of Redshift. Redshift the architecture is based on Postgres, and it is a distributed database. What does distributed database mean? It means that the data resides in multiple machines. So if you look at an architecture of Redshift, they have these machines are generally known as nodes, and there is the master slave concept. You have a leader node, and then you have various compute nodes. Now, the responsibility of your leader node is basically to do the query plans, to handle the load, to do the aggregation, the data that comes from multiple nodes, kind of sort it and aggregate it and cater to the client applications. But leader node is the one which is primarily responsible for planning your queries and passing that plan to individual nodes to carry those queries optimally. Uh, Now, the interconnection between compute nodes and the leader nodes are extremely fast because Amazon uses a very high-speed communication channel, and that's what. So not only parallelization, but also the high interconnectivity, low latency helps in fast query response by this MPP architecture. Now, Redshift, like any other MPPs, have certain characteristics of storing data. And the primary characteristic is columnar storage. And what does columnar storage mean is, if you think about an Excel sheet, right? When you read, you go by rows, right? You look at the cell and go by rows for understanding every cell. And then you go to the next row and then to the next row and move towards right. So that is the typical way we read the data, and our traditional databases like Oracle or SQL Server used to store the data that way. Okay, so a row, all the attributes of a row is stored together, and then the next row is stored, all the attributes are stored together. But when you do analytical queries, you typically go along a column. For example, you want to find an average of a price. You particularly look at a column and do aggregation on that column. Now, MPP typically stores all the data of that column, of specific columns together. So these are columnar storage. And the advantages are that it can be compressed, okay? And there are a few more advantages as well. It can be encoded, and there can be something called zone maps. You can kind of create a map of different value, create a flag at various points of the column. For example, if it's a date time column, you can create zone maps by months or years. Okay, so when you scan that column, it can skip the result. I'm seeing okay. So there is a attendance link sent by Mayank, so kindly mark your attendance there. And we're going to talk about today how Query Optimizer works, how the results are cached, and what is compile code. We're going to go into details. And few more things are the queries are handled, the load of the queries are handled through Workload Manager. We'll look into it. And integration points we have already talked about. It integrates S3, Dynamo, but the primary source through which S3 gets its data is S3. Okay, and cost-wise, Redshift, I won't say it is very cheap. It's not something like S3, but it is far cheaper than buying on-prem appliances. Like if you compare with storing data in a Teradata appliance versus storing data in Redshift, Redshift is far cheap. It's about $1,000 per terabyte per year. So a little deep dive and understand the architecture. So what I have done here is I have taken this box on the right and tried to understand it. And all of these diagrams are taken from Amazon documentation. In fact, the whole presentation is based out of Amazon documentation, even the tutorials. So here, if you look at what's the responsibility of the leader node. So leader node acts as an execution engine for the query, and it basically does the parsing of the query, generate the code, and it has different schedulers and communication layer, and route the query to individual nodes. And nodes has something, so the compute part of the node, the calculation is the nodes has is like a machine of its own, right? It has processor, it has network, it has RAM. So these are individual machines, right? And it has disks. And when the storage is concerned, the IO and the disk management, they use a term something called slices, okay? And that depending on the type of the node, you can get multiple number of slices in Amazon Compute Node. So that's about the architecture. Next, the two important concepts, and these are again refreshing. We are not kind of coaching you entirely about Redshift, but these are the important concepts when you do query optimization. The two important concepts is distribution styles and sort keys. What are these? So when you define a table, when you create a table in Redshift, you have to tell how do you want to store the data. Uh, because table is a logical concept, but at the end of the day, the data is going to be written in the slices. And you have to tell at the table design time what will be your storage style. And there are three styles. The first one is key, and key style means based on a specific column, the values will be hashed and the similar values will go to similar nodes. So for example, if you have used country as your key, and I have say three countries like India, UK, and US, right? So, and I have three nodes. So those values will be hashed, and all the values of all the rows that has India will go to node 1, and maybe UK to node 2 and US to node 3. So basically you're using the value of a column to determine your distribution. The second one is even. Here the rows are distributed in a round robin fashion regardless of particular column. So basically your entire data sets is equally distributed and it doesn't look on a specific column. And thirdly, the all. This means the entire table are kept in each of the nodes. So you have to consider your cost impact when you go for entire table, I mean all type of distribution, because you're multiplying basically by the number of nodes where you're storing the value. So the storage cost will go higher if you go for all distribution. And there is a technique which one you should choose, and we'll go through that. The second one is the concept of sort key, and this comes when the data in relation to how the data is written, and this has immense effect on disk I/O, compressions, and the query performance. So sort key tells you on which column or columns, you can have multiple columns, you want to sort your data. Now there are two types, and these icons are meaningful because a compound type works like a funnel, right? Suppose you have mentioned country, state, city as your sort key, right? So what will happen is basically it will create a map, a index where the country is defined first, and then state, and then city. Now the significance here is if you retrieve your data in the same order, okay, and you, for example, in the where clause, wherever you are specifying particular country, state, and city, compound type of sort keys will work good. But in many cases, it doesn't work that way. I mean, you want to have multiple columns, but you don't know which ones you're going to pick up or in which order you're going to pick up when you filter the data or when you retrieve the data. In those cases, you can go for interleaved sort keys. Basically, what interleaved sort keys does is it takes every column value, puts equal weightage for each, and creates a hash function on top of that to kind of basically index your data, putting equal weightage for each of the column. So that's the kind of basics of Redshift, and I will take a pause here and look at the question window before I go to the next section. Any questions you can type. Okay, I am not seeing any questions. I'm just scrolling up. Screen will share after it. Yeah. Okay, so let's proceed. So from this point onwards, if data comes in unstructured way, yeah, so some Sumit Arora is asking what happens if the data comes in an unstructured way. So that has to be curated, right? So Redshift, remember, is a warehouse platform. Okay, it can store huge amount of data, but you cannot call it a data lake to store all your unstructured data. Typically, the flow is your data. So if I go back to the where does Redshift sit, right? Typically, the flow is from the various devices. Your data it gets ingested and lands in S3, And S3 has different something called buckets, right? So there is a raw bucket when your data lands in as is condition, and then you use EMRs or Hadoop or Spark platforms to curate the data. Okay, and you can do analytics on top of that, and output of those programs also lands in S3. And then onwards, once you have your data in the same structure as the table, you push the data from S3 to Redshift using a copy command. So the requirement is in that copy command, the S3 file structure should be exactly a mirror of your table. So you cannot handle unstructured data. Basically, you can, but Redshift alone cannot handle unstructured data. You have to kind of curate their data before making it, before pushing it to Redshift. Second question, do you know any equivalent service in Google Cloud? Yeah, BigQuery. BigQuery is a Google Cloud platform. If you can, please explain the interleaved sort key again. Yes. Interleaved sort key means if you, so suppose you have, say, um, a requirement where you do not know in what order you want to um, use the columns in the where condition, or whether you will use all those columns, right? For example, these are not related, non-related columns. For example, one of the column is year, another column is country, and the third column is say product category. Non-related columns I want to sort by. Um, so in those cases, and you don't know like whether you're going to use each of these in the same order I have mentioned in all the queries. So in those cases, what Redshift does is basically take uh, create an index by sorting the data for each of these and put equal weightage. So in the where clause, if you use any one or any two or any three and not in the order that you have defined, you can do so and you can still leverage the advantages of sort key. That is what's meant by interleaved. Whereas when you go to compound, the expectation is your sort key order that you have defined in the table creation time is maintained at the query retrieval time. Dynamic creation of tables and columns. No, it is not possible. Dynamic creation of tables and columns in Redshift. You have to run the create table commands, define your columns, define your distribution key, sort key, encoding, all of those. Encoding is optional. You can do it auto and let copy command decide. But basically, you need to have a clear idea how your table looks. Of course, you can do a alter table and add columns. Those are not at all good practice in MPP. The recommended way is you create a new table and then push your data to that. But yeah, it is not comparable to something like MongoDB, where you can kind of create your keys on fly. Okay, let's move to the next section, and I will take the question after this section. From this section, we're going to dive deep, and first, what we're going to understand is how Redshift understands a query and how it tries to tune it, right? So there are two parts to it. Number one is the query processing, and second is optimizing, right? And let's see how Redshift processes the queries. So it happens in two steps, okay? And again, this is the entire leader node responsibility, query planning and execution. The objective here is you are sending some query, SQL query, through ODBC or JDBC connection, and it first hits the leader node, okay? And the output of the leader node is basically a code, a C++ code, a compiled code basically, that's sent to the compute nodes to run. Now, in the leader node, this gray box, it happens in two parts, okay? In the first part, so we'll go through each of these steps, right? So the leader node receives the queries, which I already told, and the parser produces something called a query tree. So there's a parser, and the output of the parser is query tree. And what is a query tree? Query tree is a logical representation of the SQL query that you have written, right? And then this query tree is passed to the optimizer. And the output of the optimizer is, we'll understand what is logical transformation, physical planning, but the output of the optimizer is basically a query plan, and we'll understand what is a query plan. But before we go there, let's try to understand. This is the point where you're going to tap in and try to understand how Redshift optimizer has planned your query. Okay, so there is a command called explain plan, and it is the fundamental tool for analyzing your queries. Okay, now the optimizer evaluates, rewrites. So basically, whatever SQL that you have sent, that might be kind of rewritten, and it can be basically the whole idea is make it more efficient by the optimizer, right? Now, as I said, optimizer generate query plan or plans, and then there is the execution engine, and it's the responsibility of the execution engine to translate it into something called steps, segments, and streams. And what does each of these mean? We'll look into the next slide. But on a high level, a step is an individual operation needed for running the query. The step can be combined to allow multiple nodes to perform like joins and other database operation. So let's look what each of these are, right? So each individual operation is called step, but several steps combined together is called a segment, and segment is basically a single process, and this is the smallest compilation unit that a compute node can handle. So I can give an example which is shown in the next slide, and I will explain with this query what is step, what is segment. I'll come to that. And lastly, the various collection of segments is parcelled to form something called stream. And as I said, it is a compiled C++ code base that creates these step, segments, and streams. So let's look at this. So as I said, like you need this keyword called explain in front of your queries. So you need to understand, you need to have some idea what queries are going to run on your database in order to see its performance, right? In fact, during the table design time, you need to have some idea so that you can design your keys correctly, the distribution and the sort keys. The output of this is it looks similar to this, and note that this query is not run. Okay, if you remember in the previous slide, I have shown you here something called stats, right? So when a query comes, the optimizer referred to the stats that has different information of the table and outputs that plan. The optimizer never executes the query when an explain plan command is written. The query doesn't get executed. The optimizer refers to the stats and creates this plan. Now, if you look at this plan, and don't try to read every details of it, we'll come to that later today. But if you read, generally the query plan is written from bottom to up, and there are different things in the braces, which I will explain a little later, and there are some operations written out here, right? And we'll come to those later. But this is how typically an explain plan looks like. And if you see, there are, what is happening is we are joining event and sales table, and then there is a broadcast happening. So all these operations are typically converted into C++ compiled codes, which is results in segments, multiple segments, and streams, and that's how it is executed. So we don't probably need to understand how it converts into individual segments, not required from a development standpoint, but it will be enough if you understand how the query plan looks like, right? Okay, so we said like query plan has operations, types of steps, columns and tables used, how much data is being processed, cost. So let's understand this, right? So if you look at a query plan, right, select, explain, and then the query, and you come up with get a query plan. So inside the braces, you see three things, right? The cost, okay, and then the rows, and then the width. The cost has two numericals. The first one is the first row, how much, so what is the cost for retrieving the first row? And the second one is for the successive runs, how much time it is going to take. And if you, this one is tells how many rows it gets returned, and the width is in bytes, how many, what is the byte, right? Or what is the size of the row that it has returned, right? So if you see this, the when you read these numbers, these are cumulative, so it builds on top of one another, right? So 87 to 133, so it added the difference between these two on this, and so 133 is cumulative of 83. So that's how it keeps on increasing. And alignment has a significance. If it is aligned at the same level, it says that it basically tells you it can run parallelly. If not, it will run one after another, which are serialized operations. So again, cost. Okay, one of the common question I get here is, what is this 131.97? Is it seconds, milliseconds? What is it? No, none of these. These are not seconds. These are not number of rows, bytes, or anything. This is just a number. And this number basically helps you in comparison different steps inside one query plan. If you open another window and run the explain plan again, you will get a similar one and with different numbers maybe for the cost, but you cannot compare this cost with the one which you ran again. Okay, these costs are relevant only for the explain plan that you have executed in that window. Another session will be a different one. Only relevance is comparison as you move across the same output of the explain plan. Okay. Next, there are certain operators, because you saw the explain plan, there are certain operators like this hash functions, conditions, sequence scans, and let's try to understand those. The sequential scan or seq scan indicates basically the entire table is getting scanned, right? And it is a costly operation, but you cannot avoid it. You need to read the rows, right? One of the way to decrease the sequential plan is sequential scan is the amount of data being scanned. So you do use where clause and do predicate pushdowns to limit the number of rows. The second common operator we get is the join operators, where multiple tables are being used. And out of that, the nested loop joins is the least optimal because it is resulting from a cross join or a Cartesian product due to some inequality in the joins. The next one, which is a hash join, is typically faster than loop join, but hash join also tells you that the data in your tables are getting distributed. Okay, the data movements are happening among nodes, or the data movement, one table is getting broadcasted to another place. So data movements are happening. Merge joins are the best because it means that your data need not move from one table to another. And then there are other operators which I will not go into details. I will leave the link in the section in the notes section. We went through for the data distribution redistribution concept, because now you see that you have tried to define your distribution key, right, as per your model. Okay, and then you are letting optimizer decide the data redistribution. Okay, and you hope the optimizer will honor the design that you have defined in the distribution styles, right? Now, as per the query plan, so why it is required, right? So optimizer determines where the block of the data need to be located to execute the best execution plan. The data is physically moved, redistributed during execution. If you have a good plan, you really don't need to move, right? So what is the objective of redistribution? There are two objectives, right? One is redistribution is done to ensure that the data is broadcasted, okay, but there the network latency comes into play. Okay, and the reason you would like to do that probably is to ensure that the nodes are equally utilized, right? You don't want to keep all your data in one node and kind of make one node overwork than the other. The second one on the other side of the spectrum is you want to minimize data distributions because you want to co-locate your data. Okay, so minimize your data movement, co-location of the data. Okay, so these are the two goals, and how it is done, as I said, is broadcast and redistribution. When you look at the query plan, typically one table will act as an inner table and the other table will act as an outer table. The inner table is the one which comes at the bottom of the query. Okay, it is scanned first in the bottom of the query. It is generally resides in the memory, and typically the ones which you do the predicate push downs, those will be the inner table. Just give me 1 second. I have got a chat. Okay, so this is for attendance. Sorry for the interruption. Okay. So I was talking about the inner table and the outer table. The outer table are the ones where the inner table goes to try to match the data. It typically stays on the disk, okay, and that's the table against which the inner table is being matched. Now, why stats is extremely important, because the way optimizer works is just by looking at the stats and nothing else. So it's important that you keep the stats of every table updated, and there is an analyze table command for doing that. Now, output of the optimizer is going to look like this. In fact, if you look at one of the query that I have just shown in previous slide, oops, just a second. I showed a, yeah. So here you see there is distribution style, broadcast, inner, right? So these kind of things are basically telling you what is the distribution style. So this table is extremely important for understanding your query optimization. So let's understand this. So broadcast is the worst thing. Okay, so basically the entire copy of the inner table is broadcasted to all the individual node. So um, it goes to all the tables at the query time. Okay, it's not the distribution style all. It is saying that because all the nodes doesn't have your data, the optimizer decided that it is going to take the copy of that table and going to send it to all the nodes. I mean, the inner table is broadcasted to all the compute node. All none is no distribution style required, because you have done a wonderful designing, because distribution style is already all. Already it is also you're paying on the high storage cost, but the advantage now you're getting is no distribution is required, right? None means that you have excellently designed your tables because your joins are now co-located. So how can it happen? We'll come to that. Basically, if your joining columns are having the same keys, then, and if you have used that key as a distribution key, most of the time you'll get, and we'll run a query to see this. Okay, and there is distribution style inner, where the inner table is distributed. Outer means the outer table is distributed. Sometimes it happens, very seldom. And then distribution style all inner, the entire inner table is redistributed to a single slice because the outer table is all. So yeah, so that's a bad design practice to distribute the bigger table to all. You will be paying too much on your data cost. Redshift is costly from a storage standpoint, and both tables are redistributed. So let's look at an example. I think that's the best way of doing it, right? So I will open a uh, screen here. Just 1 second. Yeah. Okay. Okay. I'll look at the chat window and see if people have any question, they're understanding what I've done so far, because now I'm going to do a little bit of Q&A. I mean, sorry, a little bit of exercises. Please ask if you have questions. Okay, so look at this. So let me first, okay, there is conversation. Just a second. Okay, so going back to my PPT, where is that? Just be a moment. Uh, okay, so there are various types of joins that I would like to go through, but before I do so, let's understand what we are trying to do. So there is a database which Redshift doesn't ship, but they will ship you all the details. That looks like a model here. Basically, it is something called ticketing database. There are two fact tables, the sales and the events, and then they have different dimension tables. And basically, it tries to look at different sporting events, the ticket sales, the ticket buys, and tries to analyze. Now, looking at the number of rows, it has got 200,000 rows in the fact tables, and there the dimension table, the number of rows ranges, right? For example, only 11 rows in the category table, whereas the user table has 50,000 rows. So when designing this database, in Redshift, you will find Redshift tutorial. They will teach you how do you determine each of your keys. Will the recording be shared? Yes, the recording will be shared. It will be, yes. Okay, so let's look at the query that we have built and try to understand the explain plan for that. So here are some of the create table scripts. Okay, so somebody asked like about dynamic way of creating columns, possible alter table, but not like Mongo where your data editor can create a table. So this is how you write your keys, right? So in the user table, you have defined your distribution key. So it is a key style distribution. You're using user ID. So same user ID will land in the same node. And this is the same column is user sort key. And similarly, the other tables are defined, right? And so that's how you, at the design time, you need to know basically your styles of distribution and sort keys. And then this is how you write a copy command, and you basically tell from which S3 bucket you're going to copy the data, and where is your region, what are your credentials, so on and so forth. Now then you copy that, and this is where you analyze the tables and keep your stats updated. I have already run this earlier for so that we don't waste time here to load the data. Uh, so these are the data loads that has happened pretty fast load times. Now after the data loading, now our intention is to understand, okay, how are these explain plan I can understand, right? Okay, so let's look at this category and event. Okay, now if you look at category and event, let's come back to the table definition and let us look at uh, categories and events, right? If you look at event ID is my distribution key. And if you looked at category, which might be a little up here, category ID is my distribution. So it's two separate things, right? So if I run this explain plan, it uses, yeah, so it uses, but it is using a broadcast, right? So here, if you see, the event is the outer table, category is the inner table, okay, and it is broadcasting the smaller table because the smaller table is typically chosen as the inner table, which is basically broadcasted to all the category nodes. So here is the way to easily see what is your table definition. So there is a table called pg table def, where you can pass the table names and get only the columns that has the keys defined. So I was using basically this to understand what are the keys instead of looking at the DDLs. But look at the another query where we are talking about sales and listing, right? So look at the sales, this one, and listing, this one, right? So if you look, the distribution keys for both of these are same, is the list ID. So this should give me a very good join condition, right? So if I run this, you see as a distile none. Okay, so it's the data are not flowing from one node to another because I have used the right distribution keys among these. Getting a chat message. Does Redshift chooses which one to mark at which. Yes, it does. Redshift chooses which one to mark as inner and outer. Typically, the inner tables are the small tables because they reside in the memory. But yeah, it is the optimizer's responsibility. And then I went for kind of adding another table on top of what I had earlier. So this one gave me a wonderful result because there's, but in event, if you go back to your table definition and do run it, right? Now I'm looking at the event. Um, so no, not this one. I'm looking at the distribution key, which is true. Event ID, okay? It's not the listing ID like we saw in listing, okay? It is a different distribution key. So what happens here if I use three table join? Okay, so let's see here. They have done event, and then if you see the join condition for sales and listing, like earlier, there's a distile none. But when you take both of these, okay, the join condition becomes bcast, so broadcast inner. So the event table is broadcasted of the result that they got from the dist none of these cells and uh, the yeah. So from the listing and the sales table, whatever is the result, that sits, but the event table goes to each of those result in each of these nodes, and then that's how this is the killer, right? But it is still good because at least two tables are kind of coming in the same node. And then you can run explain plan. The last one shows an example where you are running an aggregated hash, right? So because there is an aggregation operation. Yeah, here. Okay, so back to a slide. So, and you understand these numbers, right? These numbers I explained. This is the first hit. This is the subsequent hit. It gives a comparison. It adds on top of one another from the previous step. These are the number of rows returned. This is the bytes. Okay, so going back, what I just told you is explained in each of these slides. Okay. Okay. So now we need to go towards what can we do to improve your query performance. There are basically 8 points to improve your query performance. We talked about it in some way or other so far. But let's try to recap that, right? And each of these has links here. So if you want to dig down deeper, I will pass this slide and click on these. It will open the Amazon documentation where you can understand it more. Nodes, processes, and slices, I will not repeat it further, but basically based on how many nodes you have more parallelization power, but it also means that you are paying more money for that cluster. So make a balance there, right, between your performance need versus how much you want to spend. And it basically you have to understand the architecture part to understand, and also there is a calculator to understand how much each node cost. Now, when I say nodes, and when I say how many nodes needs to be chosen, right? So I have just clicked on the link on the Amazon pricing, right? So they generally publish their pricing with type of node. So one is called dense compute node, which are compute intensives. And the other one is called dense storage nodes. And storage nodes are where you have huge amount of data. The DC and DS comes from those notation. And 2 is the generation number, right? It's a second generation machine. And then dot, whatever is here, is kind of size of the node. So you can compare it to your apparels like 2x, 3x, 4x large. Amazon has for dense compute large and 8x large. Basically, it is on loose terms, it will tell you like you have 8 times the power. Yeah, okay. And then their pricing out here. So based on your requirement, you have to select the right node types that will give you basically what is the CPU and other things, and pricing comes into play. Data distribution we discussed in length, right? Sort key also we did discuss. The size of data is extremely important. So in one of the best practice, which I'll show later, always determine the size based on how much data you really need in the query. Okay, I have seen data warehouses, tables where are like millions of rows, even billions, right? So there is no point just by saying that this table has 30 million rows and this is the biggest table. No, you need to really look at the query, and as part of your technical consultation, ask like, what is your hot data? How much query you really need, how much data you really need, and then determine which are your data sizes. And about concurrent operations, how many queries can hit the database at the same time. It is handled by something called workload manager. Okay, and there is a concept of slots, uh, and basically there are certain number of slots that can run parallelly, and beyond that number, if there are further queries coming, they have to wait in the queue. Now, what happens if there is a very long-running query blocking a slot, or there can be multiple long-running queries blocking a majority of the slots. So what happens for the short-running queries? Will they wait? So those are the discussions around concurrency. The answer to this question particularly is no, they don't have to wait. Redshift now has something called SQA, or SQA, yeah, Short Query Accelerator, that monitors your query performance, understands through a machine learning algorithm what kind of queries takes you typically run, and typically what is the runtime it will keep on recording, and automatically route your short queries to dedicated SQA slots. Um, and then we talked about the query structure. We'll see it, the query running best practices, and the code compilation you also need to understand, because whatever is the output of the execution plan, right, that is stored in the memory as LRU cache. Okay, so the second time run is extremely important. So very important when you do try to analyze the query performance. Uh, do not run the explain plan once and determine your code. Always run explain plan twice. And in a specific, to be very specific, the number of connections you have. For example, one you have ODBC connection, another one you have JDBC connection, right? The LRU for both will be different, right? So do not do a explain plan using ODBC connection and say it will be applicable for a JDBC connection. Okay. So how do you do how the code compilation happens, and where you apply your understand your explain plan result is important. Okay, so there are. Let me take a tap on the time and let me see. We are almost an hour. We're going very slow. So let's see how much we can cover here. So analyzing query. So make your table designs better. I talked about deleting your unnecessary data. Vacuum is a command which is very similar, conceptually very similar to a disk defrag, right? So when you do lot of updates or deletes or inserts inside your table, you should do a vacuum to reclaim the space and resort your rows. Okay. Analyze, on the other hand, updates your stats table so that your optimizer can use the proper latest stat of the table. So always run um, analyze after you do a vacuum. Vacuums are typically done once in a week. I wouldn't recommend running vacuum on the entire database. Run it on table by table, because vacuuming on entire database takes down the database for many hours. Okay, your database is open, but it will become very, very slow. Okay, so this point I mentioned, right? Run your query once for every type of client, basically ODBC, JDBC client, so that the the queries are compiled and cached. So there are log tables that can help you to identify possible issues, and explain plan we talked about. If you want to go deeper inside the explain plan, these are the two system views which you can use to get more information about your query optimization. Okay, we are getting into section 3. We don't have much time, and I'm afraid how much time we have for the tutorial. I will take a break for a minute or so here and look at your questions. Let me know if anybody has any questions. I'll scroll up to see if there is. Yeah, the session is getting recorded. We'll pass on the link. Does Rashid chooses which one to mark? Yeah, we answered this. Yeah, you can put your questions if you have any, or else I will proceed with the presentation. Can't hear anything. Am I the only one? Um, yeah, so let me quickly check my microphones. Yeah, these are all unmuted. Okay, there are others who can hear. Okay, so Ashish, you might want to check with Mayank. Okay, yeah, so I think others can hear. So, yeah, Ashish, why don't you check with Mayank um, or rejoin? Sometimes rejoining is helpful. Okay, let's go back. I heard another beep. Just 1 second. Let me quickly check. I'm getting multiple beeps here. I think I hear that. Okay. Okay, so there is one question. Vacuum versus analyze improve query performance? Yes, both improves query performance. Why? The purpose of vacuum is to reclaim your holes, in lack of better word, that got created due to operations like delete, update, or inserts, right? Or the kind of haphazardness that got created because now you insert a new row and physically the sort key which was there, you're not putting that data into the same block, right? So in order to reclaim those spaces and arrange your sort keys, and if required, that the redistribution doesn't happen right through vacuum, but you, at the insert time your data should go to the right node. But in order to do kind of a maintenance housekeeping, vacuum is very important. Now the purpose of analyze is just to get your stats table updated so that your optimizer has got the latest stats, and it can create the best query plan. Okay, hope that answers your question. Let me now move to the next section because we are really running short on time. Okay, so tools and best practices. Now I'm going to talk about three best practices. One is for designing the tables. The second one will be for loading the data. And thirdly, for your query designs. Just a second, I'm getting few more questions. Yeah, it works. Okay, sorry. Okay, now for table design best practice, we talked about it, right? How you're going to choose your sort key. The rule is like this. Okay, so as part of your technical consultancy, look at the queries and figure out, do you use timestamp column? Can you segregate in most of your queries, segregate what is your hot data, and is do you and mostly does your query joins with the timestamp? So if so, use that timestamp column as the sort key. Okay. Secondly, which columns are going through range filtering and equality filtering. Range filterings are greater than, less than kind of conditions. Typically, sort keys works best when you have contiguous data. For example, a numerical column, right? So if you have, and the reason here is I mentioned about zone maps, and because Redshift stores your data in columnar fashion, and I'll take an example. For example, age. Okay, it's a number, a contiguous, maybe a contiguous number if your data is has high cardinality. Okay, and then it will kind of create a range at put a flag at different like ages 0 to 10. This is my zone 1, and 11 to 20 zone 2, so on and so forth. So whenever you run a where clause, it can kind of skip the block and go to the right block if your data resides only on a few zones, not that it doesn't have to enter scan everything. So figure out which columns participate in such kind of range filtering or equality condition. Okay, and After you have done this, the third one that you should look, the indicator that you should look is basically which columns are now participating in joins. And it really works well if you have the same column as your distribution key um, as a sort key. And why? Distribution key, if it is the same column of the both the tables which you're joining, if you have the same distribution key, it helps you to get your data co-located. So both the tables, the same data is residing in the same node. You achieve the data co-location. Now for joining also, it can skip the entire sort plan, the sort phase and the sort merge phase, and your data is like one to one arranged in ascending order, right? So this results in a merge join in Query Optimizer and returns your data extremely fast. So this is the third indicator, how to choose your sort key. How to choose your distribution style. Okay, now the whole goal here is I want to minimize my redistribution because network movement of data is the slowest in my entire chain, right? Now, remember that you can have only one column if you go for a key distribution style. And the first pointer is what is, if I have a fact table and a dimension table, I'm talking about dimension modeling here, where you have a fact table and you have multiple dimension tables around it. If you have a fact table and a dimension table, use the common columns for those for joining. Okay, typically a fact table is gigantic, and the biggest dimension table, if you can co-locate that data, use that column. So that, but again, the definition of largest dimension table, okay, varies, right? Because what is the largest dimension table is only determined after you filter your data set. Just do not look at the table size and say, this is my largest dimension table, okay? In fact, I have a picture to kind of explain this, right? Yeah, here. So look at this. So this is a fact table and I have multiple dimensions. Now look at this. I have chosen a disk style key for D1, though D2 is a bigger table, but the data that I'm using from D2 is very small. So in reality, D2 is not my biggest dimension table, right? So the definition of largest dimension is a little tricky. You need to really figure out from technical consulting what your data, your clients are using, right? Another point of caution is this distribution key that you're choosing, it should be of high cardinality. Now, why so? Suppose I have like 10 nodes and I have chosen gender as my distribution key, which is a low cardinality because it can be male or female, I mean, for simplicity. And then I will be using all my data goes in node 1 and or node 2. And node 3 to node 10 are all empty, right? So if your data is skewed and has low cardinality, then you're really not serving the purpose of parallelism, right? So that's another point which you should check. Your data has a high cardinality if you're going for a key distribution. Okay, so once you've determined your key style, key distribution style, then for the small dimensions, typically, for example, the calendar table or the lookup tables, right? You can put a distribution style all because number one, even if it multiplies in every node, the entire table, the cost won't go very high because the table itself is small. And secondly, from an optimization standpoint, the data is readily available in that node. There's no network transition to happen. And thirdly, the ones which are left over, right? Go for an event style. So unfortunately, you can have your queries require different join keys. So these are called surrogate keys. An individual dimension have their own surrogate keys. You cannot have all the surrogate keys under the distribution style. You have to choose any one, and the one which you'll choose should be your biggest dimension table, and be aware about the definition of biggest dimension. Okay, next point is when you run the copy command, and we'll see today, I think I showed you how the copy command looks like. You can let the copy command decide what kind of compression it will apply for the column. So there are two things. One is at the table definition time, you can say for every column what can be the compression. It's up to you, right? You can do that. But You may choose to ignore that, I mean, not mention your compression type at the table creation time, but during copy, let Redshift do that decision, okay? And why are we recommending that let copy make that decision? The reason is, uh, in some cases, right, particularly, I think I haven't gotten example out here. Oh, not this one. Yeah. Okay. So in some cases, if your the column that you compress is too much compressed, right, and it participates in joins, okay, and too much compressed compared to the other columns because it's of different data types, then you will not get the best performance. In some cases, it is better to leave certain columns uncompressed so that the scans can run more efficiently. But still, if you want to determine your own compression, define the compression on your own, there is a command called analyze compression, and you can use this against every column, and figure out what is the best compression that you can apply there. Note that if you already have a sort key, analyze compression won't work, because sort keys are anyway compressed. So you have to make the sort key raw. You have to remove the compression from the sort key, maybe take the data to another table and then do the analysis. But the best strategy is let copy command decide at the first load runtime to define the compression for your table. Okay, there is a concept of primary foreign keys. Only difference in Redshift is those are not enforced, right? People who worked in Oracle, they will see errors like you cannot insert a data in your child tables because there is not a corresponding primary key. Okay, so foreign key primary keys, these are called enforcement while inserting the data. Redshift doesn't have such enforcement. However, you can define primary and foreign key for in Redshift, which will be used by the optimizers. Okay, so in that query, in that stats table, these information are kept and plays a vital role. Okay, next point is many of us has a habit of kind of defining, say, varchar 255 for all text fields, kind of practice, right? So don't do that. I mean, profile your data, add a room of 10 to 20% on of your largest length of data, typically the varchar column, and define that and until that size. Do not blindly put 255. But Redshift, for Redshift, it doesn't matter, right? It basically compresses your column very effectively. So even if you put 255, if your column has 2 characters, it's kind of going to compress that and ignore that 255 to 253 space it has blocked. So why are you still saying that do not blindly do so? Because of this reason. So intermediate query processing uses something called temporary tables, and temporary tables are not compressed, and unnecessary large columns will be using excessive memories and temporary disk spaces, which can affect your query performance. Basically it says like those compression advantages you only get at the final table, not at the temporary table which are used in between running the queries. Date time. So wherever you get date times, store them as date time. It is more effective than storing as varchar. Okay. Questions. I think we will go to the loading best practice, but if you have any questions, let me take a look at the chat window. Good question. If you can change the sort key if you have not defined properly, yes, but not through alter table statement. What I typically do is create a table with the right sort key and then do a deep copy from the earlier table to the new table. Any other questions? I use the word deep copy. We will come to that in this section. You will understand. Basically, deep copy is basically a bulk copy kind of command. We'll show you. Okay, let's proceed with the slide content. we are 20 more minutes away. I am not very sure if we'll do the tutorial. I can leave both of that for you. Okay, so each of these again has link. So when you get the slide deck, click on these, and these are very huge documentation for each of these topics you can go through. Okay, so using copy command, I say that's the recommended way. Updating. So, for example, when you click here, right? Let me show you here. So it will open the individual documentation. Uh, just a second. Yeah. So updating tables with DMLs, basically it is saying that the insert, update, and delete can modify rows, but it's going to create more holes in the tables, basically. So vacuum and analyze are recommended. They strongly recommend copy command instead of individually running DMLs to update table and insert table. Okay. And then let's talk about the deep copy for a moment. So deep copies are cases where you want to recreate and populate your data by using bulk insert methodology. Okay. So if you want to move your data from one table to another, the best thing is if you have your original DDLs, you can use a create table, a copy of that table using that DDL, and then insert into the new table, the copy table, select star from that table, and then drop your main table and rename your table copy table to sales table. So that's a very straightforward technique typically used in many places. But what happens if you don't have a DDL present, right? You can use a statement called CTS. CTS is the last one. So you can use the create table like. But create table like has a disadvantage. It doesn't inherit the primary and the foreign key. So you lose that information. But it inherits the distribution sort keys, not null constraints, right? So the syntax, instead of create table name, use like create table. So this is the table name that you like, and this is the keyword like the original table name, right? And then once this table definition got created, and this definition carries over the distribution and the sort and null constraints, not the primary and foreign key. Basically, you insert your rows like you did earlier, drop the table, alter the table. Okay. This case holds good if there is you don't have the original DDL. But there is a third option which is known as CTS, create table as, and the syntax goes like that. So create temp is the name of the table, the as select star from. So it's one statement where you're kind of creating that. You can truncate your sales table, insert just like you did earlier, and drop the sales temp table. But here there is a risk of data loss because you're kind of truncating your original table and inserting data into your new table. In between this time, if there are data write operations happening, you're losing that data. So use this CTS with caution. There is a risk of data loss. And the other disadvantage is you do not get to retain your dist and the sort key, but you can retain your primary foreign key. Hardly this is the typical way that we do use it, or else we go for this. Okay. Okay, I would like to talk about this multiple table in breaking your data into multiple tables, some of the best loading practices, right? It always refers back that you should design your queries and the table designs correctly, copy command, but use a single copy command from multiple file. What does it mean? S3 can store files of 0 byte to terabyte range, 5 terabyte, I believe. But you should basically split the files into multiple, basically splitting the files and zip it before you run the copy command. And why it is so? The reason is during copy, you can take the advantage of parallelization. Okay, and then every slice will work in parallel to get the data loaded inside them. So the number of splits that you should do should be the multiple of number of slices you have in the cluster. So remember that number of splits should be multiple of number of slices that you have in the cluster. It's not a mandatory condition. If you do so, your loading performance will be faster. In fact, the tutorial that I have is going to show you that. Now, the question is, okay, how many multiples, right? If I have 4 node cluster or a 2 node cluster and I have 4 slices, right? How many shall I do? 8 parts, 16 parts, 32 parts, how many? So that depends what is the size of each file. And Redshift, initially the documentation says it can be between 1 MB to 1 GB after compression, each of the part file, but the best performance is seen between 1 MB to 125 MB. Okay, so try to keep your files within 1 MB to 125 MB. Ensure the number of files is multiple of the number of slices you have. Okay, so that's the point. Compress your file. So you see this is a command like when you copy time from this, so it's a table name from this location, it's a LZO compression, and so you mention the compression type while loading the data in the copy command. Okay, use a manifest file. So what's the problem with this statement, right? So you copy to the table name from this, and you have mentioned the security credential. The problem here is if my file, so it's going to go to the my bucket, okay, in S3, and try to look at all the files that begins with cast data, right? Say I have like multi-part file, cast data -1, cast data -2, cast data -3. It will load, and that's good. But suppose I have got cast data -log, and which is basically a log file, right? It will try to load that as well. And that structure is not never going to match my table structure because it's a log file, and then it's going to bomb, right? The enter copy command is going to bomb. So the best practice is use something called manifest, and you mention the manifest keyword here. You mention your manifest in a JSON format so that it exactly knows which file to copy, right? So cast data 1, cast data 2, cast data 3. So now you are specifying exactly this file, not just go with a cast data wild character. Okay. The other typical problem this happens is in high-speed read-write. S3 can handle 5,000 writes per second. Okay, so if there is such high velocity data flowing in, if you do not mention the manifest files, there is a huge risk of rewrites happening. So eventual consistency problems happening because S3 is eventually consistent. Okay, so same data can get loaded multiple times, or there can be a case of missed loading. So verify your load, typical, right? Multi-row inserts. So instead of writing insert and again insert, you just write all the inserts together, right? And bulk inserts. So we saw that deep copy kind of commands, right? And load your data. So when you prepare your data, try to prepare it in the sort key order in sequential block. If you, for example, if you have time series data, so that your data table is partitioned by, for example, one table for a particular year, right? You should create your data files in search order, right? Okay, there is no merge operation in Redshift. Upsert operation, you basically have to go through a staging table and maintenance window. Okay, I have to quickly check on the time. I think we are 10 minutes, about 12 minutes away. So I will leave. Okay, so let me pick up the ones which are more important because we are running against time. Why avoid select star while designing queries? Because suppose your table has, say, huge number of columns, and if you just blindly do select star, you probably don't need all those columns, right? So you don't need that query to go to every node to pick up all the information. Specify the columns that you need. Maybe those columns are residing in a handful of nodes, right? And on the same line, use case statements because you're kind of trying to filter down really what you need from MPP, and that's typical of any MPP. Cross joins, obvious, try to avoid, because nested loop, when you see in the query query plan, that's the slowest join. You sometimes use subqueries like this one, right? You are using a subquery for getting the sales ID. This is helpful, okay? Instead of writing, you can do the same thing with a join, right? This is helpful as long as the subquery result returns less than 200 records. possible use predicate push downs. Basically, push your where clause to the compute nodes, to the slices, so that the data retrieval is minimal. And there are advantages like you can use leverage zone maps, restrict data sets, and skip large block scans. Okay. Sometimes many people use functions because Redshift supports UDFs. Um, so do not write any functions in your uh, predicates. Um, Another point, suppose you're using multiple tables and so here it is an inner join, right? So even if you mention one filtering condition, it should be good enough. But in case your other table, the sales table, has a similar filtering condition, do use that. So the data scans in these tables happen individually, and the data scan time will be less. Okay, so whatever tables you're using, if there is scope of predicate push down, try to use that. Similarly, group by clause, if you're using, um, if you know your original sequence, um, go ahead and use the compound. But if you do not, use for interleaved. Go for interleaved sortings. And if you use order by along with the group by, it gives a better result. So do not change this sequence, right? Group by BCA and order by ABC, it's not a good query. If you maintain the same order, it is better. Okay, I have just two more slides and I'll take a pause then. So I talked about the workload manager, right? So when multiple queries, concurrent queries hit a Redshift cluster, how does it happen, right? So it happens that there is a concept of service class, okay, that where you can define certain parameters. So what does this mean? This means that you kind of define for each of the queues. So there are queues, right? There are 8 queues, including the super user queue, right? That handles the query. So these are like pipelines, right? Now get inside one pipeline. So if you go get inside one pipeline, so this is one of these, right? Say Q1, right? So you have you can define how many queries should run concurrently through that pipeline. Okay. So in this case, if I have defined the blue ones, which is basically the Redshift default, right? I am saying 5 queries can run parallelly, right? And 5 is the Redshift default for number of concurrent slots per queue. Okay. So and I can define 7. Okay. So including the for super user queue, you can have only 1, right? So you can run these number of parallel queries, but there is a limitation of total number of parallel queries that can run across all the queues. Okay, and that limitation is 50. Okay, so maximum number of concurrency level across all the queues is 50. So you can say that I don't need Q2 to Q7. I will only define one queue, and I want to define 40 or 50 concurrency here. That's approach 1. Approach 2 is you can have multiple queues and split your concurrency, divide your concurrency. Note that the resources are allocated at the queue level. You can say I can allocate so much RAM on Q1 versus Q2. Okay, you can say I want my query 1 always to go in Q1. You can say all the queries launched by so and so user group should go through query 3. So those are the different rules that you can mention in your service class. But rest of the queries, you may throw more queries to your Redshift cluster, but they have to await. Those will have to wait behind the concurrent queries. So if this query 1 gets completed, this thing gets in, right? So there's a pool of awaiting queries against the concurrent queues. Okay, and then there is a tool. This is in beta. So if you open Redshift cluster, there is something called an advisor, where you select the cluster, and it gives you a suggestion, right? What are the different best practices you can pick up to kind of enhance your cluster performance? Okay, so that brings me to the end of the slides. I have 5 minutes, and I have two tutorials. One, I kept it as a homework. Let me see if I can take some questions here. Will you share the PPT along the recording along with the PPT? Yes, I will. Both PPT and the recording will go. Can you change the sort key? I think that question I have answered. Okay, let me quickly go to one of the tutorial. Okay, and so this is a fantastic tutorial on table design, and it is going to take long time, right? To do. In fact, if I do it in a classroom session, it will take around um, 2 hours. First time you do it, it will take 2 hours. If you know Redshift, it will take an hour and a half. So basically, and each of these are again links. In your free time, you can go through each of these steps to understand what you're doing here. But here is the idea, right? You have a data model. Okay, you're going to create your uh, table definition first time without worrying about keys and sort keys. Okay, and then what you're going to do is you're going to load data into this tables. Okay, and then you're going to note your time, how much time it takes to load your data. You're also going to see what is the size of each of the table, right? This is what the size is. Now you are going to look at three queries. In fact, one of these in here in the test baseline establishment, there are three queries which Redshifts. I mean, you can come up with any query, but for this tutorial, there are three queries, different patterns of queries, which you're going to run explain plan on, and you're going to see that in some cases they're using the fact tables order date, yellow order date, right? In most of the cases for predicate push down. And then you're going to decide which tables I should pick up as my largest dimension table, okay? And all through explain plans. And you are going to determine your distribution style for all the dimensions and the fact, and then there is an exercise around compression, which are the compression techniques you're going to use. And then you're going to flush all the table, in fact, drop the tables, recreate with the best practice, with the sort key, distribution key, and reload the data. And then compare your results. And here is what I found when doing so, right? So anyway, I will not zoom here because things are written out here, right? So the loading time increases after I apply the sort key. So this benchmark before and after, this one is yeah, these are for the individual table. This is storage, and this is the loading time. It became 18 seconds when I applied the sort key and the distribution key, and compressions, right? But the advantage I got in the runtime is tremendous, right? So before applying the best practice, after is after applying the best practice, and first compile and recompile. It's not pre-compile, it should be recompile. So first compile and recompile are the like first time I run the query and I'm expecting the results to get the optimization to get cached, the execution plan will be cached, and this is the time it takes. Now look at this, right? So for the first query, it gave me 90% improvement. Okay, so I leave to you. All the details are here. You will understand why the compression time increase. I mean the loading time increases because of the compressions and other stuff. Why there is a storage requirement, storage space goes down because you applied compression, and then you are going to kind of do a query. There is a query included here with the tutorial that's going to check your skewness of the data, and lastly, you're going to figure out how do you determine the keys to get such kind of advantage. 71% in total increase in the time. Sorry, decrease in the time. Now look at this one. This is another tutorial. Again, I will leave it to you. It's a very easy tutorial, but this tutorial goes through various syntax that you're going to use in the copy command. Let me give you a glimpse of that by, yeah, showing it here. And I'll just I'll not run it now, but basically there are various steps. So here I am just creating some tables out here. Okay, plain tables, nothing to do with best practice and other stuff, right? I'm creating the tables. My intention here is around loading, right? So The first thing that we try to do is we're going to kind of run a plain copy command, try to load a part table from this file, right? Pass the credential. We'll face an error. And then this is the query that's going to help you understand why the error occurred. So this is a big query. I mean, a lot of fancy stuff. Amazon gave this query. I typically don't run this query. I used to select star from STL load errors. STL load errors is the query that will help you to figure out what went wrong during the load time. Okay. Now, why don't I do that? I mean, we are just on time. Let me ask you, can I extend the session by 10 minutes up to the participants? If yes, then I can go through, maybe like 5 minutes will be enough. Okay, okay. Vijit, Gordhan, everybody's saying, yeah, yes. So let me take you through this loading. At least from this session, you'll learn how to run the copy command to load the data. Okay. So I'll come back here. Okay. Basically, I will drop the table and then I will recreate the table. I'm not worrying about the keys because my intention is not table design here. So I'll just run it. Okay. Uh, Table got created. Let me. Oh, this is the reason I'm not expanding the entire window because I cannot see. Just give me 1 second. Let me resize it. Okay, everything got created. You just want to see all the scripts ran successfully. Okay. Next is the copy command, and I will take you through different steps. Right? Okay, so I have different tables. So first I'm trying to learn what is happening if I try to just run a load. Okay, I hit an error. I hit an error. It says that invalid operation failed. Check STL load errors. The way I do it is basically select star from STL load error, but this is a fancy query on that same table that Amazon gave us. I should have truncated it. Yeah, so this is the error that came up, right? Null text missing new line. So the reason it happens is because there is a null, N-U-L, note that it is not N-U-double-L, it is N-U-L character in the text file. N-U-L is a UTF-8 character that typically gets created when you create these files, right? But NUL is not same as NULL. Okay, what copy command tries to do is it reads it as end of line characters, okay, and breaks that line and tries to process rest of the information after that as a second row, okay, and it cannot, okay. So you have to let the copy command know that whenever you face such cases, treat so here is treat null as a particular ASCII character, okay. So if I run this same thing with this option, so if you go back to my slide, I gave you all these options here, right? You see, here is the syntax of running copy command: copy table name, optional column list from the source credential, and options. These options are written here. Each of these are linked to individual pages. You can click on these and understand what each of these options are, and we are exploring some of these now. So if I write null as this ASCII character, it will go through and interpret that NUL as null, and it has loaded all the records, right? Now let's see another kind of problem out here, right? So now I'm trying to load the supplier table, right? Now here what I'm trying to show you is use of region in many cases. So if you know cloud, right, they have divided the geography into regions, and the services they launch are typically within certain regions, right? So this is a region named US West 2. If I have my Redshift cluster in a different region from where my S3 bucket is, right, then inter-region data flow has to happen, right? It's not recommended, but in some cases you don't have any other option, right? Because inter-region data flow not only contributes to latency, it will increase your cost, okay? So, but in case you have to handle such inter-region cases, right? So you can run, you can mention your region, and even if, so this is a sample bucket in US West 2, whereas my Redshift cluster is US East 1. Okay, so I will run this. Let's see. It'll not execute. It'll fail. I know. Oh no, it'll execute. Yeah, it will. Supplier goes ahead well. This is just a demonstration of how to use region if your Redshift is in a different region. So while this is loading, let's also look at some of the other options like fixed width. Okay, so 100,000 got loaded, fine. Okay, so now let's come to try to load the customer table. So in customer table, I'm trying to load the same way, but here I'm giving an option of fixed width, and I'm saying that these are my width of every column, so only load up to that, okay? And this is going to bomb, okay? So it has failed, okay? And you can go to STL load error to see the details. Okay, I can do so, but what was happening here is there. Okay, so I'll come to manifest little later, but look at this. So I know there is an error. Okay, it has error, but can I allow some errors to go through and still load the table? Okay, so if you want that option, that okay, I am okay with allowing 10 maximum errors. Use something called max errors. Okay, and then in this case, I'm running the same command, but now I have mentioned max error 10. And it says that 7 errors has errored out. Okay, now I will run again that fancy query. I run typically a select star from, but these are the problems that has happened, right? These are the problems. Sorry. So there are different levels of problems that has happened with this. Number one is invalid supported UTF-8 characters, and I will show you exactly which character is having the problem. Okay. Let's see. You see this one? These kind of characters, there is a dot out here in one of the customer, which is customer ID 1 that did not get loaded. So if you go back to the query, it will even tell you which row. Yeah, so this line number 1 has this unsupported characters. This dot is a UTF, is a multi-byte characters. Non-printable characters for which it is not getting loaded. Okay, it's not supported UTF-8. Now, Redshift supports multi-byte character. What does multi-byte character mean? In English, any such like n, right, or any alphabet, okay, results in a byte. It's a single byte. But if I go for foreign languages, okay, one such character, one such visual character will require more number of memory space to store, and Redshift supports up to 3 byte characters. Okay, so my point is, how do I handle multi-byte characters? Okay, there is called accept inv. Where is that? Yeah, accept inv cards, right? So accept inv cards, sorry, here, means that whenever you face such situation, replace individual bytes with the character that I'm giving you. So let me try to load this with this option, accept IMV cards. Okay, so it will say that yeah, I have loaded the records, but I have replaced those characters, multi-byte characters, which I couldn't handle, with this cap character. Okay, and for your information, you're going to find this the replacement that has happened in STL replacement table. Okay, so and if you look at, I don't know if there are too many records. Yeah, here. So it says exactly what it replaced, right? Now, if you look back into the same record, right, the customer ID 1, which was given problem. So here, if you see this address, which was giving problem, now you see this cap characters, right? Those dots must not be dots, must be something else, which is a multi-byte, right? Now got replaced with caps, okay? And the number of such characters, replaced characters, will appear depends on the number of bytes it's replacing. Okay. Lastly is date time, handling date time. In many cases, you get file where the date time is little inconsistent, right? the format of which is inconsistent. So the suggestion, there is an option called date format auto, where Redshift will determine and kind of adjust the format of the date time. So you can use um, something like auto to load your tables. Hmm. So that's about the date time. And the last piece is around multi file loading versus a single file loading. So I don't know why it's taking so much time for just for the calendar table to load. Yeah. So this option and this command in line 123, what I'm showing here is you have done a compute off for a single file. So it's not uploading. Yeah, it's not complete. Where is that? Yeah, this is the single file. So yeah, you're loading, and I know this is about a 12 GB file, right? And it will take about 48 seconds. I kept the result that I ran last time, right? Um, Whereas if I run the same command against multiple files, right? If you go to this S3 bucket, you will see after TBL, there is -1, -2, -3. So all those files will get loaded with the same rest of the parameters, right? It's going to take far less time. And in my last run, it took about 14 seconds, right? So I will start the loading and come back to it to see the result uh, after 48 seconds. I will also look at the queries if there are any. I'm looking at the chat session parallelly while this thing loads. I need to draw, but I'm like, fine, I will send you all the links. Yeah, go ahead and type your questions because we're already over time, and I think I answered the sort key question. Let me know if you have further questions, and let me come back to see if it has loaded the data. Oh, 35 seconds. Another 10 seconds, I'm expecting the data will get loaded. It's loading quite a huge number of record, right? 1, 2, 3, 4, 5, 6. Yeah. Quite a huge number of record, but it took 55, almost 45 seconds now. What happens if I try to load the same table um, from multiple files instead of a single file, right? It should come back within 14 seconds or so. So that's the kind of loading improvement you get by splitting it into multi-part files. We're 12, 14, yeah. Okay, so you see the kind of loading time differences that you get using multi-part files. Okay, so I think that's the one of the tutorial I wanted you to kind of show. Sorry, I don't have the time for this, the previous one. This is more interesting. When I shared this, go through these links to do your tutorials. And there is a tutorial on WML. Try doing that. I don't have the content here. And then there is a concept of spectrum, which I was working on, a tutorial on that. So I will not do those. Here are the references, okay, for all the materials. Most of these were taken from Amazon. I mean, 99% of this. I think that's all I have for today. I will just look for the, oh, how exactly do I do the multi-part in the bucket? Yeah, you need to mention that your partitioning strategy, basically doing the multi-part in the program that creates your files. You remember I said like the way we put the data in S3 is we have a raw zone, and then you have a curated zone, and then you have a load ready zone. Okay, so these are the buckets inside Redshift. Sorry, inside S3, right? S3 has these buckets, right? Now, between each of these stage from raw to curate and then curate to load ready, right? You use some programs like a Spark program or a Pig program or some kind of programming language to manipulate your data. And in this programming, in this part, when you go from curate to load ready basically means it's ready to be loaded to Redshift, right? So before you put it here you say that you determine your partitioning strategy. You can say create files by dates or even minutes and so on and so forth. Any other questions you have? So sorry, I went 15 minutes over the time, but thanks. And I request you to please share the feedback. The link for the feedback is sent somewhere here. I think attendance is there. If not, Mayank will be sending the feedback link. But do mark your attendance if you haven't already. Oh, thanks for attending. You have a good day or good evening, whatever, from wherever you are. Bye bye. Thanks.